Okay, let's unpack this. Have you ever hit the back button in your browser and just sort of wondered how it works? How it magically takes you back?
Or maybe using undo in your text editor.
Exactly, that kind of thing.
Right.
There's this really fundamental idea in computer science making that happen, often totally behind the scenes.
Yeah, it's one of those concepts that's, well, surprisingly simple, but powers so much complex stuff we rely on. It's called the stack data structure.
A stack, right. It's like a core building block. And to really get a solid understanding of it, what it is, how it works, why it's so vital, we're going to dive into some great material today using insights from Hello Algo.
Yep. Our goal here is to really walk through it step by step so it clicks and, stays with you.
We want this one to stick. So we'll cover the basic definition, its main actions, then peek under the hood at how they're actually built.
Comparing those building methods, yeah. And finally, look at some really important real-world places where stacks are just essential.
Sounds like a plan. So let's jump right in. What is a stack at its very core?
Okay, so fundamentally, a stack is a linear data structure. Think of it like items in a list, one after the other.
Okay, linear, like a sequence.
Right. But the key thing, what makes it a stack, is this very strict rule about how you access those items.
A strict rule, huh? What's the rule?
It's called last in, first out, LIFO.
LIFO, last in, first out. Okay, break that down for me. What does LIFO mean practically?
It means exactly what it sounds like. The very last thing you added to the stack is always the first one you have to take out.
The last one in is the first one out.
Precisely. And the classic analogy, the one Hello Algo uses too, is thinking about a stack of plates, like at a buffet.
Ah, the stack of plates, yes. You always put a clean plate right on top, don't you?
You do. You wouldn't try and slide it into the middle or grab one from the bottom.
No way, the whole thing would tumble over.
Right. And when you need a plate, you naturally take the one right off the top. If you wanted, say, the third plate down, you'd have to take the top two off first.
Okay, I see. So that adding and removing only from the top is the LIFO rule?
That's it. And that physical top of the plate pile, that corresponds directly to the top of the stack in programming terms.
And the plate at the very bottom is the bottom of the stack. Makes sense.
Yep. And those actions, adding a plate, taking a plate, they have specific names when we talk about stacks.
Let me guess. Push and pop.
Exactly. You got it. Adding an element to the top, that's called push.
Okay, push onto the top.
And removing that top element, that's pop.
Push and pop. It feels pretty intuitive with the plates in mind. Add top, remove top. Simple.
It really is. And while push and pop are the defining operations, most stack implementations give you a few other handy tools.
Okay, like what? What else would you typically find?
Well, besides push to add and pop, to remove, you almost always need a way to just look at the top element without actually taking it off.
Ah, like checking what kind of plate is on top without grabbing it.
Exactly. That operation is usually called peek, or sometimes top.
Peek. Got it. And these operations, push, pop, peek, are they
Right.
usually fast?
That's a crucial point.
Mhm.
Yes, they're typically designed to be extremely efficient, generally constant time, which we note as O1.
O1, meaning it doesn't matter if there are 10 items or 10 million items on the stack, adding one or removing one takes roughly the same, very short amount of time.
Precisely. Super fast.
Yeah.
You also usually find ways to check the current number of items on the stack, maybe size or length.
And a way to tell if it's empty, right?
So like is empty or empty. Very useful.
So the core toolkit is push, pop, peek, size, and is empty. And it sounds like whether you're in Python using a list or C++ with its std.stack or Java stack class, the names might vary slightly, but these fundamental ideas are the same.
That's absolutely key. The concept is consistent. And often, like you handed out with Python lists, you don't even need a dedicated stack object from a library.
Oh.
You could just take a general purpose structure, like an array or maybe linked list, and simply discipline yourself or design your code to only use it in a stack-like way, only adding and removing from one end.
Restricting yourself to just those LIFO operations.
Exactly. You're essentially layering the stack rules on top of a more basic structure.
Which, I guess, leads us straight to the next big question. How are stacks actually built? If they aren't always their own special thing, what are they made from underneath?
Right. So the stack concept, LIFO, that's abstract. To make it real on a computer, you use those foundational structures. Hello Algo shows this nicely. You can build a stack using either a linked list or an array.
So the stack is like a restricted interface on top of an array or linked list.
That's a great way to put it. You're shielding the user from operations that aren't LIFO. Let's look at the linked list way first.
Okay, how do you make a stack from a linked list?
Well, the standard Most efficient approach is to use the head of the linked list as the top of your stack.
The head. Interesting. Why not the tail, the end of the list?
Good question. It comes down to speed. Adding a new node or removing the first node, the head, in a linked list is typically a very fast O1 operation.
Yeah.
It just involves updating a couple of pointers.
Mm.
Doing the same thing reliably at the tail can be much slower, sometimes ON, because you might have to walk through the whole list to find the end first. By making the head the top, our stacks push and pop get that nice, efficient O1 speed.
I see. So to push a new item, you just create a new list node and make it the new head of the list.
Exactly. The new node points to the old head, and the list head pointer now points to the new node. Instant top element.
And to pop, you just take the current head node, save its value if needed, and then update the list's head pointer to point to the next node in the list.
Precisely. The old head is effectively removed, becoming the popped element. The diagrams in Hello Algo really illustrate this pointer juggling well.
Yeah, visualizing the head changing helps. Okay, so that's the linked list approach. What about using an array?
With an array, the convention is usually to treat the end of the array, the element, with the highest index as the top of the stack.
So if my array has items at index 0, 1, and 2, index 2 is the top.
That's the idea. So to push, you simply add the new element at the next available index, effectively appending it to the end.
And pop just means removing that last element.
Right. You remove the element at the highest index.
But wait, standard arrays usually have a fixed size, right? What if you keep pushing and pushing and you run out of room in the array?
Ah, good point. That's where you need what's called a dynamic array. Think Python lists or C++ vectors or Java array lists. These aren't fixed size.
Okay, dynamic arrays. How do they work?
Under the hood, when you try to push an element onto a dynamic array that's currently full, the structure handles it automatically. It allocates a new, bigger chunk of memory.
Bigger. Like how much bigger?
Often it might double the capacity. Those strategies vary. Then it copies all the elements from the old small array location over to the new larger one. Then it adds your new element at the end.
Wow, okay. So it does a bunch of work behind the scenes, but as the person using the stack, I don't have to manage that resizing myself.
Exactly. The dynamic array handles the growth, making it seem like the array just keeps expanding as needed.
So linked list uses the head, array uses the end with dynamic resizing. These seem like the two main ways to build a stack.
They are the primary methods, yes.
Mm.
And they both work, they both give you that LIFO behavior, but they have different performance characteristics, different trade-offs.
Okay, let's compare them then. Linked list stack versus dynamic array stack. What are the key differences?
Well, first off, functionality. Both can easily give you push, pop, peek, size is empty, all the standard stack stuff.
Right. Although with the array, you could technically access stack 0 or stack 1, right? Even though you shouldn't if you're treating it as a stack.
Precisely. You could, but it violates the stack principle. If you're using it as a stack, you stick to the top. Now, the really interesting part is time efficiency.
We said push and pop are usually O1. How does that play out here?
Okay, for the linked list implementation, adding or removing at the head is pretty much always an O1 operation. Just fiddling with pointers, it's very consistent.
Consistently O1 for linked lists. Got it. What about arrays?
For the array-based stack, adding or removing at the end is usually O1, and often very fast in practice. Arrays store elements next to each other in memory, which computers are really good at accessing quickly, good cache performance.
Usually. What's the catch?
The catch is that resizing we talked about. When the dynamic array has to grow, because you pushed onto a full one, that operation allocating new memory, copying all in existing elements, takes ON, time, proportional to the current size.
O1. That sounds like a potential performance killer. A single push could suddenly become slow.
It can, for that specific push. But here's the clever part. Because dynamic arrays typically double their size, these expensive ON resizes happen relatively infrequently.
Ah, because you create a lot of empty space each time.
Exactly. So if you average the cost over many, many push operations, the total cost is dominated by the cheap O1 pushes. The ON cost gets amortized or spread out. So we say the amortized time complexity for push on a dynamic array stack is still O1.
Okay, so array, mostly O1, very fast, but occasional ON spikes that average out to O1. Linked list, always O1. Very stable, no spikes is one. Just faster.
Not necessarily clear-cut. The linked list gives you that stable O1, which can be important in real-time systems, maybe, but creating new nodes, managing pointers, that has some overhead. The array operations, when not resizing, can be incredibly fast due to memory layout, maybe even faster than the linked list's pointer operations, especially for simple things like numbers.
So linked lists might have slightly higher constant overhead, but is predictable. Array might be faster on average, but has unpredictable spikes.
That's a good summary. Hello Algo points out that for basic data types, the array might win on average speed. It's a classic trade-off.
Wow, okay. So performance is nuanced. What about space? How do they compare in memory usage?
Another great question, and again, no single best answer. The array-based stack, especially after resizing, might be holding on to a lot more memory than it's actually using. If it doubled its capacity, it could be half empty, but still occupying the full larger space.
So potential for wasted space in the array's capacity.
Yes. On the flip side, every single element you store in a linked list stack requires extra space, not just for the data itself, but also for the pointer or pointers that link it to the next node.
Ah, the pointer overhead.
Right. If you're storing lots of very small items, that pointer overhead could add up significantly.
Okay, so arrays might waste space in unused capacity, while linked lists have a consistent per item space overhead for pointers. Neither is obviously better.
Exactly. The choice really depends on your specific situation. How big are the things you're storing? How much does the stack size change? Is predictable performance more critical than potentially minimizing peak memory usage? You really have to analyze the context.
It's fascinating how these seemingly simple choices in how you build something have these real practical consequences.
Absolutely. And understanding these trade-offs is vital when you're designing efficient software.
Which brings us perfectly to the payoff. Why does all this matter? Where do we actually use stacks? We started with browser history.
Yes. Perfect example. When you visit web pages, the browser can push each page's address or state onto a stack. Let's call it the back stack.
Okay.
When you hit the back button, what does the browser do? It pops the current page off the top of the back stack.
Revealing the previous page underneath, which is now the new top.
Exactly. Hitting back is literally a stack pop.
Okay, but what about the forward button? If I just popped something off to go back, how can I go forward to it again? Did it just disappear?
Ah, good point. If you only had the back stack, it would be gone. That's why you need the second stack.
Yeah.
Let's call it the forward stack.
Two stacks. Okay.
When you hit back, you pop the current page from the back stack, yes, but you also push it onto the forward stack.
Ah, so going back saves the page onto the forward stack.
Right. Then if you hit the forward button, the browser pops the page from the top of the forward stack.
And pushes it back onto the back stack
Yeah.
and displays that page.
Precisely. The two stacks work together. Going back moves items from back to forward. Going forward moves them from forward to back, both using LIFO perfectly.
That's clever. And undo-redo in software is similar.
A very similar principle. A stack tracks the actions you've performed. Undo pops the last action off and reverses it, maybe pushing it onto a redo stack. Redo pops from the redo stack and reapplies the action, pushing it back onto the undo stack.
Cool. Now, the source also mentioned program memory management, the call stack. That sounds deeper.
It's absolutely fundamental to how most programs run. When your code calls a function, the system needs to keep track of where to return to when that function finishes, plus manage that function's own local variables and stuff.
Okay.
It uses a stack, the call stack, for this. Every time a function is called, a block of information called a stack frame is created and pushed onto the call stack.
A stack frame, what's in that?
It holds things like the function's parameters, its local variables, and crucially, the return address, the spot in the calling code where execution should resume after this function completes.
So if main calls function A and function A calls function B, you get a stack frame for main, then one for A pushed on top, then one for B pushed on top of that.
Exactly. B is at the top. When function B finishes, its stack frame is popped off the call stack.
And the system uses that return address inside B's frame to jump back to the right place in function A.
That's precisely how it works. And when A finishes, its frame is popped, returning control back to main. It's perfect. LIFO. The last function called B is the first one to finish and have its frame removed.
Wow. That explains so much. And this is especially clear with recursion, right? Functions calling themselves.
Oh, absolutely. With recursion, every time the function calls itself, a brand new stack frame gets pushed onto the call stack.
So if a function calls itself 5 times deep?
You'll have 5 stack frames for that function piled up on the call stack, plus the frame for whatever called it initially. This buildup of frames during the recursive calls is the descent.
And when it starts return?
When the base case is hit and the recursion unwinds, each function return causes its corresponding stack frame to be popped off. This ascent or backtracking phase perfectly mirrors the popping sequence of the call stack.
That connection between recursion and the call stack push pop is really illuminating.
It really is. It shows the call stack in action, managing the flow and state using that fundamental LIFO principle.
Okay, let's try and summarize this deep dive. The stack. It's a linear structure, super important, defined by last and first out.
LIFO is key. Add to top, remove from top.
The main actions are push, add, pop remove, and peak. Look, usually very fast, O1.
Plus size and is empty for convenience.
And under the hood, you build them using either a linked list, using a head consistent O1, or a dynamic array, using the end amortized O1, but with potential resizing spikes.
Right, each with trade-offs in time stability, average speed, and space usage pointer overhead versus potential capacity waste.
And these stacks aren't just theoretical, they're critical for everyday things like browser back forward, software under radar.
And, fundamentally, how programs manage function calls via the call stack, which is especially visible with recursion.
Getting these building blocks solid really does help understand computing at a, well, much deeper level, doesn't it?
It really does. It's foundational knowledge that makes so many other concepts make more sense.
So as you think more about stacks after this, here's a little something to chew on. We mentioned the browser needs 2 stacks for back and forward. What if it only had one? Imagine you go page A, B, bash C, D. Then you hit back twice, so you're on page B. What's on your single stack now? Just A. What happens if, from page B, you click a new link to page X? Could you ever get back to C or D using a forward button? How does that single stack strict LIFO for limit things?
Or, think about those implementations. If you were writing software for, say, a tiny embedded system with very tight, maybe unpredictable memory limits, which stack implementation would you lean towards? The array, which might suddenly need a big chunk for resizing, or the linked list, which uses a little extra memory for every item but grows more predictably? What's the priority avoiding those big allocation requests or minimizing the constant overhead? Makes you think, doesn't it?